All right, after running a logistic regression model that we had for our example, now let's discuss the performance measurement in logistic regression. A couple of actually measurement we discussed before. If you remember that, we discussed AIC, we discussed the lower the AIC is the better. We discussed pseudo R square, which actually measures the difference between the model that we have to what we don't have any parameters and run the model over just one, a null model. And also we discuss p-values and z-values. As you can see here, for every estimate, we can get a p-value that gives us the quality of this estimate. So whether the estimate is actually, it has actually a good power of estimation, and also the standard deviation of estimate is low. So you know that there are two sources of actually increasing and decreasing in z-values or t-values in both cases for linear regression and logistic regression. That in one case the estimate is not actually strong, and the other one is actually, it has actually good explanatory power, but the standard deviation of estimate is lower. So that's the case in any case of this one, whether the source is just the magnitude of estimate or standard deviation. It's a model's call to see if they need to do extra tests and see, for example, if they can run the model in different sample and see that they can observe lower standard deviation, for example. And there is no actually predefined threshold that say, all right, p-value of over 5% or 10% or 1% is actually better or not. So it's, again, it's modeler's call to define that. Let's run for another example and see, beside those parameters that discuss, what are the other parameters that we can use to measure the performance of the model. Here, I use the dataset from Caret library, German created, and I call class age, amount, and duration. Class is good or bad of actually created quality. Ages and amount and duration are not binary variables, they look like a continuous variable. And I change the class to 0 and 1. You don't need to do that if even you use a class as a string. The GLM function is smart enough to identify that actually is a two-level class, good and bad. But the reason I use 1 and 0, I want to make it clear and transparent. So which one is good, which one is bad, because if we just go forward with that one, we don't know whether good is 1 or bad is 1. So it's a little bit confusing. That's the way that I prefer. But again, you don't need actually to do that. You can run the model right away. So let's actually call our data set. And when you look at our data frame here, you see that we have class 0, 1, 1, 0, 1, age, amount, duration, and based on what is reported here, we have 1,000 observation of these in our data set. Now we can run the model as explained before. Running logistic regression or binomial logistic regression is pretty straightforward. We define our data sets, response, and the predictors, age, amount, and duration. And again, the family of distribution is binomial. So here, what we have actually, we get the summary of the result right away as well. Let's run this code and see the outcome. So first of all, you can see that just talking about z-value, for example, we see that the p-value of all estimates is very low except for amount. So we see that here it's very high. And this is the place that you think about, all right, so why that actually is so high? We see that the estimate itself is really, really low. So apparently amount doesn't have any explanatory power. So here, for example, the outcome is something 0.00003. This is the estimate. And when we look at the range of the amounts here in our data sets, amount is something, let's sort, maximum I have for amount here is 18,000, 18 or 19,000, something like that. And if I multiply that number, the multiple of even the maximum to this number, we see that the impact in odds ratio is very, very low. So that's actually, we can see that, yeah, based on the z-value and the explanatory power of amount, probably I don't need this variable in my model. We have, again, the null deviance and residuals, same thing, but this parameter also helps you out to have a good insight about the quality of your model or the performance of the goodness of fit. But probably the best way is just look at the outcome of the model and compare it to real outcome. So let's do the in-sample test. I can run the prediction based on response because I would like to get the probability. And if I look at the class hat here, here is the class hat, right? So as you can see, these are probability like 24%, 43%, 33%, so on and so forth. And here I can actually have the ROC curve and see the quality of this outcome. And what is ROC curve? As you can see here, we have two axes for ROC curve. I have specificity and sensitivity. Basically, the the ideal fit is that I have something like, an L shape for this prediction. So it means I have a straight line here and actually a horizontal line here. Then the area under curve comes to 1, which is the ideal way. And why this is ideal, that means when I have this straight line here over here, it doesn't matter that I define any threshold. I have distinct explanation for response of event and non-events. So if I move from, for example, 20% threshold to 40% threshold, still the outcome is clear for me. So it means I have a very nice distinction in my outcome, and this is the ideal way. But usually it's not the case. Usually when we define different thresholds, we make a compromise between just losing some events, or let's say false negative and also false positive. That means if I define a very high threshold, like 80%, 90% from my response, of course, when I get actually the outcome, because this threshold is really high, it's really true, I reduce the false positive. Whereas because I have very high threshold, I lose a lot of events which are legitimate, but I assume that actually as non-events. So I have also some false negative. So that's actually the compromise that I make between these two events. So, and it's usually the case. So it's very important that we define a good threshold. And what is the best threshold then? Again, it's a modeler's call. Or maybe it's actually it's an expert judgment. It needs some business intuition. One of the ways that you can define the best threshold, for example, here is just you define a cost function. Just give you an example of, for example, a fraud in a bank. We build a model that is a binomial logistic regression to define whether this transaction is a fraud or not. So if one cost function of just not identifying the fraud transaction is bank responsibility, when it's a fraud, we just execute the transaction and the client lose money. So that's the cost, and probably bank is responsible for that. So it has actually direct costs, it has reputation costs, for example. There are other costs involved for this one. But say, all right, so this cost is really high, then let's reduce the threshold. Then we get, when we reduce the threshold, we get some actually false positive. That means the transaction is really legitimate, but we assume as a fraud. Again, there is a cost behind that. What is the cost? The reputation, the inconvenience of the clients. Clients just call, they say, or why this transaction is blocked. This is actually, I know actually is a valid transaction, for example. So again, some costs are involved on the other side as well. So it comes to which side is more important, and make a good balance between two. And of course, the first step is just make a model with a very like closed L shape with high area under curve, like for example 0.7, 0.8, to have actually the best fit. But after that, again, it's modeler's call to find the best threshold. But if you want to just have like a pure mathematical definition of threshold, you can use the function of print threshold of the best. Then it gives you the number that you can find the best threshold just mathematically to find the best result in your model. And when you just having, so the RRC curve, or you look at the area under curve, this is one of the way that you see how actually your model performs. And by the way, let me reemphasize that all these measurements are in sample. So it's the best way is actually that you do it in sample and out of sample. You can also generate the confusion matrix. So what is confusion matrix? This is exactly, you build a matrix between different type of events, which the outcome should be 0, and we observe 0. When the outcome should be 1, we observe 0, or in opposite way, or when we expect 1 and we get 1. So these are the number of the events that we see based on this threshold, when we define the threshold as 0.5. So when I change this number to, for example, 0.7, you can see we see different numbers here. So let's just keep it as 0.5 and see what we can get from confusion matrix. So first of all, again, these are the different type of response that we can compare. We can get accuracy of the model. We can see the sensitivity, specificity. These are actually different type of ratio of, for example, true positive over positive, or true positive plus true negative over all observation. That those actually are numbers, just some different parameters that you can actually see in the help file, or you can Google it and just see what is the meaning of that. But also here, as you can see, I just replicated some of these outcomes. For example, for accuracy, here I have 35 out of 60. 35 is all true, so it was expected to be 1 and we get 1, plus 673, we expect 0 and we get 0. If we sum them up and divide by all events, this is the accuracy, 0.708, and you see actually it's reported similar number here on top. So you can replicate the outcome also as you wish. But one parameter that I would like to discuss here is a kappa. Kappa is actually define the differences between observed accuracy and what is the expected accuracy. And of course, the higher this number, it means actually the difference is larger, and it gives us actually some good measurement of quality of fit. Usually, as a rule of thumb, kappa greater than 0.75 looks an excellent, but again, there is no particular number that see which one is the best. But the good thing for kappa is gives you just some sense compared to expected accuracy, because sometimes in your data set, it doesn't mean that you have actually a good distribution of events among your parameters. Again, as a rule of thumb, statisticians believe that for each actually parameters, if you have minimum of 10 events, that's the best way, but this probably is not the case. Maybe you have very limited number of events, then again, the expected accuracy actually is lower. So kappa gives you a good sense of observed accuracy considering the expected accuracy. That's why actually I like this actually measurement as actually one of the parameters to measure the quality.